Hello, good day. My name is Sean Persad, and this is our group project for COM 2601. My section of the project was question one, where first I broke up the topic into three main parts: the process of performance techniques, the performance laws, and benchmarking. I focus on understanding how these ideas connect rather than treating them as separate topics. Secondly, I worked on the topic of improving processor speed. I learned that processor speed isn't about just the clock rate, it's about how efficiently the CPU handles data. I understood SIMD execution, where it lets one instruction process many data points at once, but my colleague Machi will further discuss this. I found out how hardware accelerators like GPUs and TPUs handle specific workloads faster than CPUs. I learned that pipelining and out-of-order execution keep the processor busy by overlapping instructions, and also realized that performance must be balanced. If memory or input-output can't keep up, even the fastest CPU slows down. So it all has to be balanced. Third, it was Amdahl's and Little's law that I worked on. Amdahl's law taught me that there's a limit to speed up. Even small serial paths restrict total performance gains from parallel cores. I understood that to get real benefits, you need to minimize the serial portion of a program. And for Little's Law, it helped me to see how throughput and concurrency are connected. To keep all cores active, the system must handle many tasks at once. Together, they explained why parallel systems still depend on smart workload management. Finally, it was benchmarking and spec. I learned that benchmarking measures performance fairly using controlled, repeatable tests. The spec benchmarks test both single-task and multitask performance using real-world programs. And finally, understanding that high spec scores mean a system is balanced and efficient, not just fast in one area. I could pass you on to the colleague Matthew.
Hey, good night. My name is Matthew, and today I'll be presenting on accelerated computing. First of all, I was speaking on SIMD. What is SIMD? SIMD allows for a processor to execute one instruction on multiple data elements simultaneously. This improves computational efficiency by reducing repetitive loops and maximizing CPU utilization. This approach increases CPU saves energy and speeds up data-intensive operations such as multimedia and scientific computing. Next, I'll be talking about how the CPU and GPU architecture differ. CPUs are optimized to sequential tasks by using smaller number of powerful cores focused on low latency, fast memory access. GPUs, on the other hand, contains many smaller cores designed for massive parallel execution, enabling them to process large volumes of data simultaneously. Their architecture and memory systems make them better suited for high parallel workloads like graphic rendering and machine learning. Furthermore, I'll be speaking about LPUs and TPUs. A TPU uses or a tensor processing unit uses stylistic arrays to reuse data efficiently for tensor and matrix operation, while LPUs focuses on energy efficient, low latency processing for machine learning. Furthermore, these accelerators deliver higher performance per watt than traditional GPUs, making them better for AI and deep learning workloads. Lastly, I'll be speaking about Amdahl's law and the limitations of parallelism. According to Amdahl's law, overall speedup is limited by serial portions of a program. Technologies like SIMD, GPU, and AI accelerators address these by maximizing parallel execution and reducing serial bottlenecks. SIMD, in particular, minimizes the serial code by processing multiple data items simultaneously, while GPUs and specialized accelerators improve computation, efficiency, and memory usage. Techniques like these, such as gradient checkpointing and high bandwidth interconnects, further optimize performance in large-scale AI and computational tasks. Thank you.
Hi. My name is Sean Caruth, My section was question 3, and I'll be talking about the volume and bottleneck with respect to performance. As we are aware, modern computers are based on the volume architecture, which serves us well, but is limited to a problem called the volume bottleneck. This refers where both the data and the instruction share a pathway for transfer, and this shared pathway limits the rate of transfer for both. To mitigate these issues, the architecture has evolved in many ways, with a few being cached, where frequently stored instructions or data are stored close to the CPU. Another being parallelism, where processors use pipelining to overlap the execution of instructions. Another way engineers tackle this problem is to develop new architectures. One of being the Harvard architecture, which separates the pathway that instructions and data travel on, allowing for simultaneous fetching of instructions and data. This architecture was able to somewhat tackle the bottleneck issues. However, it greatly increased hardware complexity and it had inefficient memory utilization. So it was not able to become the preferred architecture, but a concept is used for the transfer of data instruction for cache memory. Another architecture is the data flow architecture, where the instruction is executed based on the availability of data rather than by a program counter. This gets rid of instruction sequencing, but next issue this get rid of instruction sequencing bottlenecks. However, the instruction cycle is inefficient, resource allocation is complicated, and memory manipulation is not an easy task. And finally, the architecture with the most potential, quantum architecture. This uses quantum mechanics, which the transmission and manipulation of quantum bits between locations are processed simultaneously. The major issue is that qubits are susceptible to environmental disturbances, leading to errors and decoherence. Through all these innovations, the effects of the von Neumann bottleneck has lessened, but still limit the capabilities of computer architectures. Now, I send to my colleague who could tell you even more about quantum computing.
Hi, good day. My name is Valmikki Ramnath, and thanks, Sean, for passing me on. My section was question 4, which is based on quantum computing and quantum architecture. So we start off with qubits. Qubits are basically the quantum version of classical bits. They can be either 0, 1, or both at once through superposition. This allows much more information processing at the same time, together with a lot more storage capabilities. Sorry. Qubits can be broken down into two parts. There are physical qubits and logical qubits. Physical qubits are basically the real devices, and logical qubits are the combination of many physical qubits using quantum error correction to stay stable. Qubits interact through gates and are protected by error correction and are controlled by classical hardware. Secondly, we continue with quantum gates. Quantum gates perform operations like classical gates do, but they add the element of superposition and entanglement to it. Entangling gates such as CNOT links qubits so the state of one affects the state of another, which is essential for quantum algorithms. These gates are reversible, allowing manipulation and reversibility without destroying the data and the quantum state of the entire of the qubit. Thirdly, we move on to quantum error correction. Qubits are fragile. Quantum error correction keeps the computations reliable and stable. Using this quantum error correction utilizes something called ancillary qubits and syndrome measurements to detect and fix errors without collapsing the entire quantum state of the qubit. This is run by classical processors, which run the error decoding algorithms in the real time to correct errors that are detected. Lastly, we move on to classical control. A classical processor manages all of the qubits operations, sends control signals, and handles the feedback. Next, we move on to the key differences from the classical counterparts. Right? So we start off with information. Classical bits are either 0 or 1. Qubits hold superpositions and entanglement, so they can be either 0, 1, a combination of the both. Operations. Classical gates are not reversible. The quantum gates, however, are unitary and reversible, which allows for you to recover the original state of the qubit without destroying the quantum state. Lastly, we go on to the execution. Classical CPUs process sequentially. Quantum circuits apply all the gates simultaneously. Thank you for listening to our entire presentation. This has been the COM2601 Computer Architecture group presentation and poster.